expert.
Okay, I think we're ready to get started. Thank you so much to everyone for joining us. There are 39 people here, and I'm super excited for this, the world's first virtual WACI. I wanted to welcome everyone to Virtual Lausanne. I'm sure you've been enjoying the Swiss delights over the last couple of days. I also want to say a thank you to Jim and also to Luis and Karin. Of course, just for doing everything, especially in this ridiculously complicated time, but also for, I think we're all feeling a lot of gratitude right now for making the call relatively early to go virtual with ASPLOS instead of like figuring it out a couple of days beforehand. It seemed like kind of risky and uncertain at the time, but like it obviously was the right call, and we're all really grateful to have had the time to prepare. So with that, I just want to make sure that everyone has all the snacks that they can possibly desire. If you have cheese, please enjoy the cheese during this talk. It'll enhance the experience and make it seem slightly more Swiss. I also want to let you know that this is being recorded, so like, you know, don't do anything too crazy. We're planning on putting this out for all the people who couldn't be here synchronously on YouTube, along with the rest of the recordings for ASPLOS. I want to talk a little bit about logistics for questions and such. So the way this is going to work is I'm going to in fact, I'm going to do it right now. I'm going to mute everybody. And I will forcibly mute people who forget to mute themselves. And then I will let individual speakers go. If you want to ask a question, don't just unmute yourself. The protocol is going to be that you ask a question text-wise, and we'll relay it one way or the other. So here are the options. You can join the Slack channel. So if you're in the ASPLOS Slack, there is a WACI channel that you can join into, and you can ask questions there. And you can also ask questions in the Zoom chat window. The Zoom chat window is kind of like janky and weird, which is why I'm also recommending this Slack option. In either case, there's sort of two options. One is that I might select your question and read it aloud, just convey it for you if it is like a good question and phrase in a way that I think it can convey. Or if you want to, just note right in the question that you asked, like, I would like to ask this myself. And then I might be able to call on you and give you the power to speak and ask your question yourself. So if you want to do that, that is, if you want to ask a question using your own voice, just both ask your question in text and also do the raise hand feature. So the way you use the raise hand feature in Zoom is you open the participants window, which you can find like in the meeting controls in the bottom of the window. And there's a long list of all the people who are in this call. And also at the bottom, there's sort of a list of reactions. For me, it's under a little more button. You can say like, yes, no, go slower, go faster, and there's more. And one of them is wait, actually, I can't find the raise hand one. Whatever, do anything. You can do the coffee cup or whatever. That's fine. I don't know why I don't see the raise hand one in my picture. I'm going to rescind my Zoom expert license after this call. So you can do that to indicate that you want to speak out loud. So like both write down your question and raise your hand. It's no guarantee that I'll be able to call on everybody. But if you just write your question down, then we'll get at least a few people through during a question period for each. So at this point, does anyone have any questions? This is both an attempt to get me to answer your questions and also a practice period where you can try asking questions. Amrita has raised her hand and then lowered her hand. Okay, that's fine. Amrita has raised her hand again. I've unmuted you, I think. Amrita, what's your question?
So my question was about, are you going to allow people to interrupt the talk, or are we just doing a straight shot?
That's a great question. Sorry I didn't address that. Let us not interrupt the talk. So I think it would be great to just hold all the questions to the end. I think it would get to be a logistical nightmare if we tried to interrupt people during the flow of these talks, which are short. They're to be 7 minutes only. So please hold your questions until the end.
And one more question. If we run overtime, is there any way you can hard stop us, like a loud noise or something?
I can send you a lot of annoying Slack messages. That's one option. And
okay.
Also, I can forcibly mute you if you continue to go on for too long.
Okay, that would be fun. Okay.
Great. Cool. Okay, everybody. Thanks. I'm really excited to get started. Our first speaker is Amrita, who you just heard from. Amrita Mazumdar is a PhD student at the University of Washington, and she's going to tell us about some ideas involving AI and imaging and video and compression and all that. So take it away, Amrita. You can share your screen now.
Hi, everyone. Does this work?
It works.
Still works?
Still works.
Great. Okay. So as Adrian said, I'm at University of Washington. I'm a PhD student. The title of my talk is "A Picture is Worth 1,000 Bytes. Everything else is AI." So to get started, I'm going to be talking about images and video. I don't need to tell you right now that we love images and video right now. Here are some graphs that show how important it has been even before all this happened. So the annual number of new photos that has been taken globally is growing all the time. The number of billions of people on Instagram is growing every month. And a cool new one is short form video. So like your TikTok kind of short video content. People have been watching millions of daily hours of this kind of video, and that is also growing. I can only imagine in like this new world, these numbers will continue to go up. So anyway, we love images and video. They're very important to us. I'm going to be talking about architecture and systems that use and manage a lot of image and video content. So here as an example, I'm showing a cloud service used by Netflix that uses AI to understand a lot of their content in their library. So here is a system they have called Ava. And what it does is it automatically creates the little thumbnails that you see. And the way it does it is it takes any movie in their library, it automatically chooses the most interesting pictures. And then after it picks a nice one, it figures out the best cropping for that picture, and then the best coloring and color grading, and then where to place the text on the picture as well. So all this is done automatically by an AI system that you can imagine us to turn over a lot of content all the time. And this is just one example of the many kind of cloud services that run using AI on image and video. And you can also see that the machine learning stuff has gotten really good. It has done a really good job, and I really like all the pictures I see on Netflix, so I think it works great. At an extremely high level, the way a cloud vision pipeline works is I am on my daily walk, I see a picture of a cat, and I take it and I upload it to the cloud. And if I upload it to like Google Photos or something, what it'll do is it'll run a bunch of neural networks on it. And the neural networks will figure out things like the scene geometry. Are there any objects in the scene? What is the lighting? What are some of the interesting textures and things like that? But on the other side of it, we also have a cloud rendering pipeline. And that actually takes all of the things that you get out of a neural network, these features and parameters of the image. And then the goal with cloud rendering is that you can use these features and parameters with a different neural network to generate, ideally, the exact same thing out. So this is kind of like your great feedback loop of how like vision and graphics is supposed to work. We know that the vision part of the pipeline has worked really well, but what has been cool to me recently to learn is that the cloud rendering part has also gotten really good. So in this talk, I'm going to talk about feature-first visual computing. And the idea here is that I think all of these parts of the pipeline have gotten so good that we can throw out the images at the beginning, we can throw out the images at the end, and we just have to deal with features and parameters for most of the work we do every day. And so another way of saying it is we decompose all of our images and videos into learned features from AI. You can materialize the actual images or video on the fly when you need it using neural networks that we already have. And this is kind of like compression, you might say to yourself, but it's a little different. I think there are some interesting side effects that happen because we've developed so much infrastructure for machine learning already. Maybe it has more compute, less memory bandwidth, etc. So anyway, feature-first visual computing. How would it work in practice? Let's go back to my picture of the cat that I took. Let's say I take this picture, I upload it to the cloud, and it says, oh, I see you have a cat here. Maybe it's 100 pixels large. Maybe I run it through a visual question and answering service that says, I see a brown cat sitting in front of stairs and a trimmed lawn. So that's great. Maybe this is the thing. These features and parameters are the things that I actually store. I don't store the actual image. Then when I want to download it again later, you run it through a different network that looks at the features and parameters and will give me a picture of a cat sitting in front of some stairs. Maybe it's a different cat, maybe it's different stairs, but maybe that doesn't matter depending on your application. I don't know, but that's what we're gonna do. You might say like, oh, that's like an interesting idea, but I don't really think this is gonna work. The picture you showed me was really bad. I agree, but if you read recent papers, it has come pretty far. So for instance, this is from ICCV last year. They render realistic video from only learned features on an existing video. So one row here is an actual video. The other row is rendered from features of it. I don't know which is which. I've forgotten already. So, I think that works really well. This one is kind of more on the scary side. They take a video of someone doing something. So for instance, this guy's playing golf, and then they take target poses and they're able to generate new video of the person doing something different. So here he's dancing. And so this is like an example of, I only really need to store a couple of seconds of video and then poses for the rest of it, or just some sort of feature. So I think this is going to happen soon. And so, okay, let's throw out all our videos and replace them with features. What will have to change? So I'm gonna look at a couple of examples of systems that we've built that involve video or images. So for instance, storage systems. And so like this is an example of Facebook's hot and warm blob storage that they publish at OSDI. And so they have, some store for like their hot images. They have some store for like the warm images, and these are things that maybe people don't look at very often. What would happen if I also wanted to have a place that only stored features? Maybe I keep it for the cold storage, which is the images that people don't look at very often. Well, then in this data transformer part of the pipeline, maybe I would have to add a little more machine learning to do this feature-based decompression. But I think there would be some interesting side effects as well. So features are smaller, so your cold storage area might end up being a lot smaller than the rest of your storage capacity. Generating this data on the fly means I don't have to keep redundant copies, so I don't have to have like 18 different sizes of thumbnails or compression methods. You probably need to have some new data management. People have been looking at this already, but I think if you throw out the image entirely, it gets worse. And probably this decompression part of the pipeline is slow, so you might have to figure out some quality of service metrics of when this is applicable. There's been a lot of interesting work on near data acceleration using machine learning close to storage. I think this could be applied here. That's just one example. Another example is mobile cloud camera apps. So this is an actual application that I use a lot. It's an app that turns me into a cartoon. So what I do is I take a selfie of myself, I upload it to the cloud, it runs a neural network, and then it gives me this very adorable cartoon of myself on the other side. Some problems are it takes a while in the cloud, so like on the order of seconds. And then when you do the upload and download, by the time I get my picture, I've noticed that my battery has degraded quite a bit. And so this is a situation where I think, this feature-based, feature-first processing could really be helpful. So what if instead of uploading my picture to the cloud and then downloading it again, I run a neural network on my phone using an accelerator that's already there, and then only upload a small set of features to the cloud. And then using that small set of features, it gives me something that I decompress on the other side. Maybe this consumes some battery, but I don't have to upload and download as much content anymore. So maybe this is very helpful. And I save some battery life. This is great for privacy as well. I think there are a lot of security like surveillance applications this would work great for. It might be faster to run it on the accelerators on my phone than to push it up to the cloud where they're not as efficient. And I think this is a nice kind of like co-design problem of how you incorporate the accelerators you use on kind of like a compute level with the rest of your system. So, if I'm constantly using my DNN accelerator every time I want to look at my photos, what does that look like for a mobile system? So anyway, some interesting questions. There are lots of different kinds of systems that are published at conferences like ASPLOS and other systems conferences, like about CDNs, about computer vision inference, file systems, resource constrained cameras, cloud gaming, video analytics, video conferencing everyone loves now. So, maybe that's an interesting application of this feature first computing. But I think, this is going to happen, and maybe we should think about what a system that is designed for it looks like. Lots of things could also go wrong. So for instance, deep fakes are a big kind of ethical problem. I think you might have to grapple with that. If you built a system to support it, you might have mistakes. And then on kind of like a more personal note, like when does it matter if my picture is correct or not? Like with regular decompression, I don't really pay attention to this, but if suddenly a neural network was doing the compression and decompression, what would change for me personally? Would I care if it was a tourist photo? Would I care if it was a personal photo? I don't know. Anyway, just some food for thought here. Anyway, thank you for listening. I think this feature first computing is gonna happen and we should start to think about it. And I think it's an interesting opportunity to leverage stuff we've already built. So happy to talk about it more. Thanks.
Thanks, Amrita, that was great. Does anybody have any questions? I saw Mark was raising his hand and lowering his hand. So maybe as a tentative question. You can also feel free to, at this point, use the applause reaction.
There we go.
Joseph, I'm unmuting you. Would you like to ask your question?
Yes, I done me too. Okay, so for video, this is definitely a clear win I see for storage, but for images, like how much smaller is the feature data than a relatively small image? Do you actually save that much in terms of storage?
Truthfully, I don't know. I would imagine just based on like other neural networks that I've seen that it would be smaller than the high resolution images that you would see. And so you could imagine it being helpful for like lazy loading. right? Like the kind of situation where you're scrolling. For instance, Netflix, when I was doing this kind of like investigation, Netflix says that it generates like different versions of even the image thumbnails for all different kinds of mobile devices. So to like optimally compress them for the device. And so you could imagine that's a great situation for them to like reduce the amount of copies they have to have for that kind of thing, because it is kind of optimally compressed for your hardware anyway. Does that make sense? Cool.
I also have a question. Something that's always in daily life mystified me is like, if you go to a tourist attraction, you like can see just like hordes of people taking exactly the same picture. You know, like, it seems like it would be not just like very close in feature space, but like pretty close in like actual pixel space. So I was wondering if you had any ideas about how like that seems like an awful lot of like aggregate wasted energy and time also, and storage for that matter. I'm curious if you had any ideas about how to like prevent people from taking redundant pictures in the first place. Like maybe you could just recommend that like as soon as you start to pull out your camera to take a picture of this like beautiful monument or something, it can recommend, here's a bunch of pictures that are much better than the one you're about to take. Can you just imagine that you took that picture?
Yeah, or like maybe a less kind of like personally insulting solution would be it allows you to pretend you've taken the picture and that you are so great and creative. Great. But then on the back end, it actually saves the thing. I wanted to include this, but last year I was in Sweden and, you know, I was going around, I took pictures of lots of beautiful things on a film camera. And then I developed the film and I uploaded it to my Google Photos. And, you know, maybe a couple hours later, Google Photos geotagged the location.
What?
So yeah. And some of them were not that like accurate, but the very obvious monuments were accurate. And so that's an example of like, even they gave me the experience of taking the photo, but they still figured out, they did all the things they needed to do on the back end. And they probably have figured out some better transform for it that like looks like the regular one. So anyway, these are all things that I think they are secretly doing. And I think if we talked about it, we could develop some really cool systems. But
great.
Yeah.
Okay, I'm going to finally stop applauding. I think that was enough applause. Great work, Amrita. Thanks. Okay, so we have a second of 5 speakers. Up next is Prathyush Patel. So this is the second PhD student from the University of Washington in this WACI session. It's also the second speaker with the word everything in the title. I'm not sure what that means, but there's some sort of mystical connection going on here. Prathyush, are you here? And if so, take it away and please start sharing your screen.
Yep, one second. Does that work?
Works for me.
Awesome. Okay, still works, full screen?
Yes.
Awesome, great. So yeah, hi everyone, I'm Prathyush and today I'll be talking about extreme memoization, where I propose that we should store most of the computation that we do in a global lookup table. I will also be talking about extreme memoization, where I show you a bunch of memes and hopefully convince you that my idea is interesting. So let's get started. CPUs are facing a grave scaling issue in computer science today, with the end of Dennard scaling and with the slowdown of the Moore's law. But in contrast, memory is scaling with the introduction of new technologies such as non-volatile memory. Storage is also scaling. If you look at all the iPhones across the past decade, you'll notice that their storage capacities have been scaling up. And if this exponential rate continues, I predict that by 2055, we'll have iPhones that can store all of the data that we have ever generated so far in the world. Although data communication bottlenecks exist in today's systems, luckily networks are scaling and data centers have been deploying 200G and 400G links or are soon planning to deploy such high bandwidth links. And mobile networks are scaling with the promise of 5G with almost a gigabit of bandwidth. So far we are seeing a few trends. CPUs are not really getting any faster, whereas these other resources such as memory, storage, and networks are scaling up quite rapidly. This leads me to propose that we should move away from a CPU-oriented computational model into one that exploits these other resources because they're going to get faster. And one way to do this is to do extreme memoization. And the way I think you could do this is by storing most of the computation that's performed and sharing it at a global level rather than recomputing anything. The way this would work is, let's say a user wants to compute a function f of x. She might do so on her local machine and send it off to this global lookup table, which can then be referred to by anyone else who wants to do the same computation. And an obvious question to ask at this point is, when will this make sense? I think it's worthwhile to reason about this from an energy perspective, because energy is going to be one of the biggest challenges that humanity will face going forward. And looking at this across computational complexity, we can see that the amount of energy that's consumed by the CPU with increasing complexity of computation is probably going to look like an exponential curve. Whereas with memoization, this is probably going to look closer to a step function, where you pay an initial access cost for whatever you need to compute, but at some point you amortize it as you access lower levels of the memory hierarchy. And I think you'll hit a break-even point where the computational energy that's required is going to exceed the amount of energy that's required to memoize. And this is where it makes sense. I think this argument is increasingly relevant in today's world, where a lot of people are getting access to the internet and to computers, which indicates there's a lot of potential for redundancy. And all of this redundancy is just basically wasted energy. So I also think we can draw inspiration from how we have evolved as humans to look at this from energy perspective. I think human brains are extremely energy efficient because we do computation through memorization. And why not build our systems in the same way? Hopefully this convinced you that the idea is interesting, but let's take a closer look at how this might work out in practice. So the goal of the user here is to be able to memoize the function, its inputs and outputs in this global lookup table. But one of the challenges that she might run into is that the function could be implemented in a variety of programming languages. And this would create redundant copies of the same compute in the lookup table. One way to deal with this could be to compile these high-level languages down into intermediate representation and use the hash of that representation as the key of the lookup table. But it's also possible that the same function could be written in or implemented in a variety of ways. And I think we could maybe draw from research in the PL community by using equivalence graphs to store these functions. And for those of you who are not familiar with e-graphs, basically the way they work is they store a single state for all functions that have the same output. So you might be able to have a compact representation. But I think this more broadly calls for research in the PL community, where we need to be able to do cross-language program equivalence. And I think that's a really interesting problem. But once we have a way to do that, we'll be able to store key value pairs in this global lookup table that can be referred to by anyone across the world. A question that you might have at this point is whether this table is going to be extremely large. And it's a very valid concern because the computational capacity of the world is tremendously large. And if we were to run all of this compute and store all of the data that it generates, that's going to be a tremendously large amount of data. One way to deal with this could be to do approximation, where you coalesce entries in the table based on the output sensitivity. So if the outputs don't change much, you could reduce the amount of storage space that you need to store this table. And there has been a bunch of prior work on this, and it's increasingly relevant now because we have neural networks that are shown to be robust to some forms of approximation. But it's still possible that the table is going to be extremely large. And I think at this point, modern storage techniques such as DNA storage can come to our help, where you can store a lot of amount of data in a very small amount of space. The way you might do this could be inspired from the previous WACI session, where Max and Luis proposed to have warehouse scale computers of microfluidic chips, each of which can perform fast and automated lookups on DNA. And if we deploy this at a global scale, we might be able to deal with the storage problem. One of the things that I really like about extreme memoization is that it gives you this joy of sharing a compute with the whole world, but it begs the question whether sharing is safe to do. And it might not be so, because an adversary might be able to do brute force attacks on the inputs that already exist in the table, which might lead to some sort of timing-based attacks on what computation already exists. It also has interesting implications on open source code, because most functions are already out there in the public. So it might be easy to reverse engineer whatever inputs matter to the rest of the world. So I think extreme memoization brings with it a lot of interesting challenges, and some which I've not really had time to talk about are how we might be able to do efficient data delivery to users, or how to decide which functions are worthwhile to memoize. But all in all, I think that looking at the trends that we saw earlier, and to be cognizant of an energy efficient future, it's a worthwhile or interesting direction to pursue. And I'm optimistic that we'll be able to deal with these challenges, given that we've already built systems in the past which have done so. Thank you.
Just imagine that amplified many times, 53 times, Pratyush.
Sounds good. Thank you.
Does anybody have any questions?
I'll just go ahead and make, it's not really a question exactly. Okay, I'll turn it into a question. Why do you think program equivalence is the way to go? So it turns out that it's undecidable to even establish whether two grammars are equivalent. So program equivalence is definitely, it's in the same complexity class, it's undecidable. So you really end up with two choices. You have to have a very, very restricted programming language, which is more restricted than a context-free grammar, which is probably much, much less expressive than you would want. Or you could imagine something else. I just wonder whether it makes sense to actually try to push in this vision for something that is impossible. I know it's wacky, but I think that it would be interesting, I guess. Have you considered any other sort of ways of looking at this rather than program equivalence? For example, you know, if you're just memoizing the results of a function, as long as the function's side effect free, you can just have it be a key value store, which is essentially function memoization.
Yes, so I do not have much background in PL, so I did not know this, but that's good to know, so thank you. But I indeed was considering like stateless functions based on all this like functions as a service things that's been going on and being popular recently. So that is definitely like one starting point, and stateless functions seem like a potential solution there. Also, we might have alternative approaches to like reduce the amount of space that we need in this lookup table, which is like store the most popular inputs of a function. It's unclear to me how we might determine what are the popular inputs. Like it's going to be very similar to a caching policy, but maybe that's another approach to solve this.
It does occur to me also that all you need to do this is a sound under approximation of functional equivalence. That is, as long as it's sound, and it's an under approximation in the sense that it never says that two things are equivalent when they're not, then like it's just a matter of like how well you want to do. That is how close to precise you make that equivalence checker. So you could make something that is a decision procedure, but doesn't actually decide equivalence precisely. Did somebody else have a question? I feel like I saw another hand raised, but I don't know who. It was Joseph. Go for it.
Are you familiar with the short story, The Library of Babel?
I am not.
Okay, so there's this really interesting story where there is, imagine a library that has every possible sequence of characters in a book in the library. So basically all knowledge is encoded in the library. So this is sort of like a logical extreme of what you're proposing, but there are really interesting consequences. Like the only way to find a piece of knowledge in the library is to already have that knowledge, because the only way to index it when every possible string is there is to know the exact string, right? It's like it's a matter of entropy. You need exactly the information that you're looking for. So I was wondering if like, when you take this to the logical extreme, there are a lot of really interesting consequences and it kind of falls apart. But I guess this stuff about under approximation and like the, you know, kind of makes it fit. But I was curious if you had like thought about, it'd be really cool if we never had to compute anything because everything is already stored. If like in that extreme, hey, someone post, thank you for posting. Yes, it's really cool. I recommend you look it up. But I forgot what my question was when I was ranting about this.
I really like this library of Babel idea, and like I think we maybe run into something similar of a problem with extreme memoization. So I was thinking of like having a hash function for storing the program as a key in this lookup table. And one could think of like storing what the output of the hash function will be in this lookup table as well, which is kind of self-referential. And maybe that's also what happens with the library of Babel. I have not read about this, but maybe. It's super interesting.
I have one question I want to ask from Slack. This is from Shreya Singh, who asks, do you feel that this talk and the one before it is very related? And in the way that the ideas of one can be applied to another. So the question is, like, do you think that that the ideas from Rita's talk could be applied to do this extreme memoization thing?
Interesting. Okay. I suspect like we might be able to store notions of what people compute. Like, it's unclear to me what features of computation would be. But let's see.
Well, just for fun, I actually took the question a different way, which is not about featurizing the functions, but featurizing image inputs. That is, if the computation you're doing is processing images, then you could like sort of memoize the inputs in the form of features and save a lot of space, and perhaps also do this approximation thing.
Right. Yeah, like essentially they are very similar now that I think about it. You might be able to also apply it in the other way, like use extreme memoization for what Amrita is proposing. Basically where you end up like storing, like one of the arguments that I'm making is that data storage is going to be cheap. So it might not be as much of a problem to end up storing lots and lots of features which are relevant to various users. And that might address some of the challenges that Amrita thought were possible, were something we'd face in the future. So yeah, I think it's applicable both ways to some extent.
Awesome. Well, thank you, Bertush. Let's applaud one more time by pressing the button. You don't need to unmute yourself to clap. This sounds terrible, so only I'm going to do it. Great.
Thank you.
Awesome. Thank you so much. Our third speaker is our first speaker, not from the University of Washington. Our speaker is Amrita Khan, who's a professor at the University of Virginia, who has some thoughts on reviewing. Take it away, Samira. You can share your screen whenever you're ready.
Can you see it?
Yes, I can see.
Okay, thank you everyone for joining in these crazy times. So today I would like to talk about reviews of our papers. So reviews are very close to our hearts. Like we are happy if the reviews are good, but at the same time, our hearts break if we don't get good reviews. So today I will like to show one of the reviews of my work. And like any other academic who doesn't miss any chance to give a summary of their work, I will actually first give a summary of the work on one side of the screen, and then I will show the actual review on the other side. And I will exactly show 3 sentences. So the problem statement of the work is persistent programming is hard. It's because the programmers have to enforce a specific ordering, but the hardware at the runtime changes the ordering, and it's very hard for the programmers to verify if the runtime ordering would actually be the correct one. And you can see from the review that the reviewer also correctly points out that this work points out the problem of how to do correct programming for persistent memory. So then this work provides some assertions to the programmers, which they can use to test ordering and durability guarantee for crash consistency. And if you look at the review, the reviewer also correctly points out that. And the third thing is using these assertions, it's actually possible to build high-level automated checkers for transactional libraries. And the reviewer points out that this work tests for bugs, and also it's possible to automate the testing for different conditions or scenarios. So if you look at it, it's actually a pretty good review. Like as an author, I have to say that the reviewer did a very good job. But unfortunately, I lied. I lied to you. So this review is not generated by a human person. It's actually generated by a machine learning model. So GPT-2 by OpenAI is a very large language model trained on a massive data set. Basically what it does, it takes a sequence of input tokens and predicts what would be the next tokens in the output. So here in the animation, if the input is recite the first law, the model figures out that the most likely outcome is the first law of robotics, and it produces a robot may not harm any human being. So this model actually has generated a buzz. It's actually quite accurate, and people have, like the newspapers have come up with cautionary to apocalyptic headlines for this model. These include, this should worry everybody, the AI that was too dangerous to release, it's a new world, or it's actually a Pandora's box. So you can actually access the model online. Like if you just go to Talk to Transformer, you can play it around. It's actually pretty fascinating. So the question that I'm posing, that if the language models are so powerful right now, what will happen in next 30 years? So let me take you to the future. The time is August 15, 2049. It's just 24 hours before the ASPLOS 2050 deadline. The location is unknown, but you know it's a grad student's lab. So meet people. He's a grad student working on his paper for a while, and he's almost finished. He just needs to do one more thing before the deadline. So he looks at the program comedy list. He uses the reviewer recommendation system and finds out the match that who may review his papers. So essentially, people want to generate the reviews for these prospective reviewers. Unfortunately, what he figures out that there is this one particular reviewer, Nemo. He's from a different community, and there aren't that many reviews available for Nemo. And why is that important? So the models that we have now, these are generic language model, and they output a generic review. So if we just use these GPT-2N, the nth version of the model in 2049, that will not give us the individual review that we were seeking for Nemo. So we need some supervised learning to train these individual style. So what does people does? People calls his friend, collects reviews from the underground market, pays with some cryptocurrency. So now with the collected Nemo reviews, he actually tunes his language model, uses a Nemo classifier, and uses some backpropagation to make it a specialized Nemo language model, which will give us Nemo reviews. So people generate the review for his paper, revised based on the reviews, and then submits the paper on time. He's happy, he's off to vacation to Hawaii. So now let's go to 2 months later. The time is October 15, 2049. There is just 24 hours left before the ASPLOS review deadline. The location, as you know, all professors work from a coffee shop. Okay, so meet Grumpy. Grumpy has 18 papers to review in 24 hours. And obviously, he has access to his own reviews. He uses those to tweak the model for using a Grumpy classifier. And essentially, he generates reviews, which will look like it's Grumpy's reviews. However, Grumpy is known to be a really harsh reviewer, and he wants to pose as a super cute, happy reviewer. So being an ML enthusiastic, he adds a specialized mood classifier. So essentially, he tunes the model with an emotion classifier, which can generate different types of reviews with different emotions, like happy, harsh, relaxed, etc. So with this model, he actually generates all his reviews. He submits the reviews, and now Grumpy is actually pretty happy. So this is how DeepReviewing will be done at 2050. And please give a round of applause for our characters, people, and Grumpy. And now I will take some questions if there is any.
This applause is both for Samira and also for the two characters. Anybody have any questions for Samira? I personally am terrified by this whole thing, so I might be able to muster a question, but I'm busy being scared that I'm going to be out of a reviewing job. I love reviewing so much, I can't imagine someone taking it away from me, giving it to the robots. All right, I do have one question, Samira. I guess I was curious when I was watching your talk about, like, if you have any thoughts about how to take this from 2050 and bring it to be like somehow useful in the shorter term. That is, like, in a more limited way, you could imagine, like, you know, taking some high level inputs. So you train it on all your reviews. We've all written like many words of reviews to train on. But instead of generating an entire review end to end, like based on a paper or something, I want to give it like sort of a few hints here and there. And it sort of like fills in the sort of long text to make it look like my word count.
Yeah, definitely. So if you actually you go to talktransformer.com and you provide a very short few sentences, it will actually append the review with very similar sentences. So the review that I have shown, the first two sentences are actually written by human, but the third one was generated by GPT-2. And there was, so I would say that summarizing the paper, that's actually quite accurate even now. So the GPT-2, the original paper, they actually show that they could summarize quite a bit of text, and the accuracy was pretty high.
Great.
So I would say that like we don't need to go to 2050. It will happen pretty soon.
Great. Thanks. So there's one question on Slack that is a joke. It says, where can I invest in the startup that you're obviously working on? You don't have to respond to that question. It's all right. I know that like, you probably have an NDA for your startup, so we won't put you in that position. Emily asked this question. Does this mean that reviews are based strictly on reviews completed when a review is completed when a reviewer is in the early stages of their career and they're trying to generate training data? As you could have an angry grad student outlooks lingering long past when a reviewer actually has that outlook. So I think that Emily's worried that like sort of your attitudes will be kind of frozen in time, and so you as a human might have like better ideas and better attitudes in the future. But your model that you've trained is still going to be stuck on the reviews that you wrote just before the advent of the review singularity.
So I would comment that that's actually a pretty known phenomenon that people when they're in the beginning of their career, they write a lot of harsh reviews, but then with years, they become more and more relaxed and they appreciate the grand picture. But for machine learning models, I think you can always retrain your reviews. Like you don't want to train it once and be done with it. So it might not be a problem.
Sure. Brandon has a question. You can unmute yourself, Brandon.
Hey, so is this possibly like a tool to help us think? Because this is generating feedback automatically, right? Like we can take a model and generate ideas about our ideas automatically, right? So maybe this is a tool to help us think. I think that it doesn't require too much imagination to see how you could generate some text related to your paper and it might give you a different idea than you had before you saw that. And whether it's good or bad, it doesn't really matter. It just might help you to sort of freely improvise your way into a new, paper idea or a way to fix your paper or something like that. Have you thought about using it that way?
So if we just build a summarizer, I think that will help us. That will also may generate new ideas. So in that sense, it's pretty plausible. But I think here, which I didn't mention, is the ethical issues of taking other people's reviews, right? So the new reviews were not available. People we are not we don't open source our reviews, or it's not publicly available. So I think the ethical point based on the current situation in our community, I wanted to point out that if things go this way, the way people can game the system could be, the implication of that could be pretty bad. But as someone who, if I have access to my reviews, so I take that and use it to generate more ideas or the summary or better text, that seems a pretty reasonable thing to do.
Yeah, it actually seems like more than summarization might get you so far, but it seems like having the adversarial spin that comes from reviews sometimes might actually be more helpful in refining your idea or giving you more ideas. It might through the template of past reviews, you might get chiseled over just the right thing and then realize, I should fix this. That's what I should fix before I submit this.
So that I completely agree. So I actually got some advice from one of my colleagues to make sure that whatever machine learning claim I'm making is not completely ridiculous. And he actually said that once we use this kind of adversarial network and it goes back and forth to summarize and come up with good reviews, it seems like that is something will happen soon, yes.
Great. Thank you, Samira. Let's have another round of applause, virtual otherwise, for Samira. Great. I want to introduce our fourth speakers, Alon Rashelbach from the Technion. The thing that really distinguished Alon's talk from the rest of them, in my mind, is it was the only practice talk that I personally had actual psychological challenges while watching. So I think you'll see what I mean. It was really quite troubling. So good luck, everybody.
Okay, so hi everyone. My name is Alon Rashelbach from the Technion in Israel, and I'm going to convince you why putting bugs in your data center might actually be a good idea. Data centers, they are huge, massive, one of the most complex facilities humanity has ever made, but mostly power hungry. Research shows troubling facts about data centers and cooling. Up until 2006, the costs of data centers worldwide have been estimated to be more than $30 billion US. A 30,000 square feet data center consumes about $6 million US for cooling in a year. As such, data centers require massive cooling infrastructures. This is a data center owned by Google. The conventional way for cooling data centers is using heat sinks and circulating large amounts of chilled air. However, some new designs, such as Google's TPU 3.0, are already switching to liquid cooling on board. And the reason is for maximizing performance. In fact, the thermal conductivity of liquids is much higher than that of air. Liquid cooling on board has many downsides as well. It requires additional plumbing support, such as supporting pumps and pipes. It has many maintenance complexities, and most troubling are the leakage and moisture hazards that can permanently damage the hardware. We suggest an alternative for cooling data centers, which is using living spiders. Research shows that the thermal conductivity of spider silk is high and even close to that of copper, which is the second best metallic conductor. In certain conditions it even passes the thermal conductivity of copper. So using living spiders as cooling devices will reduce maintenance costs, no need to take care of pumps, pipes, and anything, is self-sustained, as spiders make their own webs and you can't hear them complaining about it. And no hardware risks, no leakage, no moisture, no nothing. So how do we encourage spiders to spin webs in a data center in a way that helps cooling? First, we need to understand their natural habitat. So spiders live in open woods and attach their webs to trees and low shrubs. Their prey consists of flying insects of various sizes, such as bees, wasps, flies, and so on. Their length is between 1 to 4 centimeters long. Their web is between 1 to 2 meters in diameter. They repair damages to the webs without disturbing the remainder. And most importantly, the bites are not dangerous, nor they are radioactive. So you won't turn into a Spider-Man just yet. So let's say you own a data center and I convinced you switching to living spiders. What do you need to do? Step 1, you need to make heat sinks more attractive to spiders. You can use branch-like heat sinks made of metal. Step 2, you need to redesign the server racks such that the heat sinks would be visible to spiders. And step 3, you need to dedicate special flying zones for flying insects for the spiders to feed on. You can use mosquito nets to bound such zones. The insects themselves could be provided from external hatching farms, and that way you won't need to control the entire ecosystem, such as planting nourishing plants, aggregating them, controlling the sunlight, and well, etc. You get the point. There are many open questions and challenges, mostly zoological, such as, do spiders tolerate the extreme temperatures that exist in data center? Do spiders get along with each other? I don't know. What do you do about dead spiders? What do you do about data center operators that are afraid of spiders? There are many other open questions and interesting facts about data centers and spiders in a short paper. Thank you.
Awesome, thank you, Alon. I thought that was a really great talk, but I had a very terrible time watching it. I hope everyone else is recovering. I have one question from Slack I want to ask first, which is from Luis. Luis asked whether, like, once you've got this infrastructure of spider webs going everywhere from rack to rack, could you also use it for data transfer, especially if your data is stored in DNA?
That's an interesting question, because this is the first lead we searched when we thought of spiders, and apparently spider webs are not conducting electricity, so you can't use spiders.
But now you have to remember this question was asked by Luis Ceze, who says, what if your data is stored in DNA?
So it could be a chemical network.
Interesting.
Yeah.
Interesting is right. I agree.
The other good thing is that I think the spiders keep humans away from the data centers, which probably is going to increase reliability in general.
Yeah. Nice.
Brandon, you have a question. You can unmute yourself and ask.
Can we just remove the spider webs from the spiders and put the spider web material in the data center and not put all the spiders in the data center? Is that another way? I'm thinking of like, it's kind of like saying we want copper in the data center, so let's roll a bunch of boulders in there. Maybe we could just like refine this material and get rid of all of the scary arachnids that are going to be biting and scaring people.
Well, you can do it, but you won't have self-sustained webs, right? The spiders are making their own webs and you don't need to pay them.
We can create a new industry of web refinement. We can have like web maintenance people that go in and like replenish the webs as we need more of them.
There's a very related question on Slack, this one from Karin Strauss, who asks, is there a role for synthetic biology in data centers? Perhaps use the fluidics infrastructure already there, presumably, and have bacteria ferment the spider webs instead of using the spiders themselves. So this is a person presumably in the same position as me and Brandon who says like, great idea, don't like spiders. So do you think that synthetic biology could be a way around it?
It's possible.
Here's another question from Akshita Sriyaman on Slack. Says, insects have been shown to cause data center failures in the past due to issues like short circuit, insulation, clogging of motors and fan drives, or corrosion. Thoughts on how we will have these spiders while still isolating them? So it's sort of, you can see all these questions are going in a similar direction with regards to the whole spider
Avoiding
thing.
spiders, no spiders, please. You can cover the racks with mosquito nets, and that way the spiders won't get in. This is a possible direction.
I see. Yes, right. Man, there's so many questions for this talk. One question that is such a dumb joke that I don't even want to read it out loud, but I'm forced to because here I am, the host. It's from Emery Berger, who says, if this is very successful, we could one day have a World Wide Web. That's not a question. You don't have to answer that. Mark Mancy asks, does normal silk have the same properties you mentioned? Do you have any idea?
Normal silk from worms. This is the...
Yeah.
I think not. The same research that was conducted on spiders noted that worm silk is not does not have high thermal conductivity.
Great, cool. Okay, we have one last question from Slack, which is a sort of semi-joke question. I'm going to be rating the level of jokiness of questions from here on out. It says, what about security? Are there potential side channels from web-to-web vibrations? I've created like an additional channel for implicit communication from server to server. Well, there's clearly a lot to think about. There's a lot of future work, especially on the whole question of like, can we have the best of both worlds? That is like having spider silk, but please no spiders. Thank you very much, Alon. Let's have another round of applause.
Thank you.
Okay, so our fifth and final talk for the day is from Joseph McMahan, who's a postdoc at UW. Joseph, you have a talk about deep faking hardware. You can take control by sharing your screen.
Am I shared?
Yes, you are. It looks great.
All right. We just got to clock up so I don't go too long here. Thank you, everyone, for tuning in. My talk is GANs for Good, Deep Faking Hardware. So first things first, I have to thank my collaborators. You know, research does not happen in a vacuum, and science is absolutely a collaborative endeavor. None of this work I'm going to talk about would have gotten off the ground without all of the incredible efforts of everyone on this slide. I'm joking, of course. This is a wacky talk. The research does not exist yet. And do you know what else? These people don't exist. Everyone on this slide is an artificial image that was generated by a neural network. These people do not exist. The collaborators are a lie. They are from a really cool website called thispersondoesnotexist.com, which is an implementation of a neural network called StyleGAN, which has been used to generate people's faces. It's been used to generate cats, molecules, and scripts of the TV show Friends, which you can peruse at your leisure. StyleGAN is a particular type of neural network called a GAN, a generative adversarial network, which is the thing that is responsible for what society now calls deep fakes. So these are things like videos where one person's face has been subbed in for someone else's face. And this is done in an automated fashion. No human had to edit the video. A neural network was able to make the substitution, and they are very convincing. It's a really scary, troubling thing that we as a society have to grapple with in the future. GANs have been used for everything from fake images and videos to financial fraud. But the question that I would like to pose is, can we use GANs for good? And more specifically, can we use them for the ultimate good, hardware design? So what would it look like if we were to GAN generate an adder? So let's say we take one of my collaborators, Margot, and Margot's going to generate some things that look kind of like adders, like this little warped adder I've got here. And Tasmin, my other collaborator, is going to take in these generated designs and decide if they're good enough or not. Now, Tasmin has got experience as a hardware designer and knows what a, quote, real adder looks like. And she's going to use that prior knowledge to evaluate these generated adders and then decide if it is good enough or not based on that. So this is exactly the setup of how a GAN works. We have two parties in an adversarial relationship, one of them generating things and trying to trick the other one, and then one of them evaluating those things based on some prior knowledge. So if we sub out these people for two different neural networks, we have exactly a GAN. A generator network and a discriminator network are what they're called, and they can be used for images, frames of video, anything that you can train your features on. And the key insight that makes GANs so cool and so successful is the adversarial relationship here. So these two networks are trained in tandem, but have exactly opposite objectives. The discriminator is trying to minimize error by correctly classifying the fake things as fake, whereas the generator is trying to maximize error by consistently fooling the discriminator. So as we train these two things in tandem, they both get better and better, and we get better and better quality fakes, which is really cool and really troubling. But anyway, back to hardware development. So we're doing this for adders. Let's say we have our crazy hardware designs that Tasmin has approved. What are the problems with our GAN adders? One big problem is that they're probably no longer precise. So if I put A and B into the adder, I might not get A plus B out. I might get an approximate answer. That can be problematic potentially. Another big issue is, how do we get good functionality out of quasi-random designs? If we just sort of generated these and spit them out of a neural network, how is this useful to us at all? How do we get good functionality? Well, there are answers to this. If it's not precise, one easy answer is, okay, let's just be approximate. Thankfully, we have hardware structures that are approximate. Things like predictors and caches don't have to be right all of the time to provide really good performance benefits. And more broadly, we don't have to be approximate if we move to a better feature space. And by that, I mean, we don't have to operate on the level of transistors and gates. We can move to a higher level feature space of things like functions and functionality, things like hardware blocks. If we train on that level and generate designs as composites of functionalities and hardware blocks, then we're in a less dense space and a higher level feature space, and we don't necessarily have to be approximate. It's like comparing an ISA to gates. It's just a different sort of abstraction. And how do we get good functionality out of our system? Well, ideally, we'll be able to configure how our training is done to generate interesting designs, which is something that I'll tackle in just a minute. But first, we have an even bigger problem, which is, where do we get the data to train this GAN? Thankfully, we live in a world of accelerators today. If you look at any modern SoC, there will be dozens and dozens of different unique accelerators on the die. And so if we consider all those different accelerators across all chips and all cores across all chips that have ever been produced, we actually have a pretty considerable mountain of hardware that at our disposal. So my first proposal here, let the GAN run free, is to unify all of humankind and collect all of our accelerators, IP blocks, and cores together, so that we can use them as training data for a GAN. I see no problem with this. This should be very easy to do, to collect all those things together. There are no legal or financial problems at all. And we'll use this to generate random hardware. But of course, the hardware isn't actually random. There'll be prototypical examples of the things that we feed in, which is a really interesting question on if we generate random hardware based on everything that we've ever built as a species, what does it look like? What does it do? Does it do anything useful? I have no idea, but I would be really interested to find out. Second proposal, which is a little more focused and potentially more useful, is to limit our training and generation to a single category. So for example, CPUs. So in our network, the discriminator is going to make sure that our generated CPUs, for example, look like real hardware and behave like real CPUs. And then we can add objective functions to our system, either on the generation potentially, if we can finagle that, or just by filtering the outputs of the GAN. And we've got objectives for area, power, timing, all the usual metrics that we care about as hardware designers. So this might potentially generate designs that are competitive in these metrics, but were generated automatically. And we can apply this to CPUs, GPUs, ML accelerators, predictors, caches, DSPs, any hardware block that you can think of. Finally, the third proposal here is the interesting one, which is the fake out. What if we use different categories of hardware for the generator and discriminator network? Which is to say the generator was trained on one type of hardware, the discriminator is trained on another type of hardware, and then we put them together and train them in tandem. So this is where we start deep faking things. What if we were to, for example, deep fake a CPU to look like a GPU or vice versa? What does that even mean? What do the designs look like, on the other end? What if we deep fake an embedded system to look like a server class huge CPU? What if we fake a single core processor to look like a multi-core processor, or some other scalar design to look like a vectorized version of the design? Or what if we deep fake an ML accelerator to look like a tiny IoT device? Do these things produce interesting designs? Do they produce functional designs? I don't know, but potentially if just any of these work some of the time, it's automated. So it's a huge win if we can get this stuff online and producing usable designs. So to wrap up, why should we do any of this? Well, I think there are two main reasons. One of them is that while humans are incredibly creative animals, it is very hard for us to think outside the box, especially in something like hardware design where you need a lot of training and a lot of familiarity with prior work to generate something new. It's easy to be weighed down by the baggage and preconceived notions in the field. But a neural network that is operating in large part off of randomness, creating designs off of random noise, we can create new functionalities that humans have never thought of yet. And then the second big part of this is that we have new demands placed on hardware constantly in terms of compute and functionality. All of the time, it's growing and growing, and hardware designers are lagging farther and farther behind in generating these new designs because it just takes a long time to develop hardware. It's a very difficult and laborious process. So if we are able to get an automated or even semi-automated way to generate good or just passable designs, it would be great. This would look something like design space exploration, but the key thing that makes this cool is we have an intelligent discriminator. The GAN actually filters designs so that we as humans, or the programs we write, only have to look at the good designs that get spit out on the other side. And that is my proposal. GANs for good, deep faking hardware. Thank you very much.
Thanks, Joseph. Awesome. We got one question on Slack so far. It's from Luis, who says, is deepfaking the outputs directly equivalent to this?
Deepfaking the outputs, like if I were writing CPU programs, just deepfaking my programs, or deepfaking the inputs and outputs of my programs?
A different strategy you could take is instead of trying to deepfake the net list of the actual hardware, just try to make something that can fake behaving the same way. So just generate something that can.
Yeah, there's definitely a spectrum here. I mean, it's not clear what the distinction would be without actually performing the experiment to see what gets spit out. There are a lot of ways to go about this. I would say, that as hardware designers, we're familiar with evaluating hardware, and hardware is sort of, I can run a range of applications on my single design, so it might be more portable and a broader thing to fake the hardware. But maybe getting more specific gets you an answer more easy, or gets you a better answer for your domain. I don't know.
Sure. One question I had, I'm just curious about your whole notion about sort of augmenting the human creativity of hardware designers. And I'm curious, it seems like in order to make that work, I really like the idea of just sort of generating arbitrary random hardware, finding out what it does and see if it inspires you. But I'm curious about that step, about finding out what it does. So say I've got some arbitrary weird hardware. My question is can I build an interpretable description of what this thing is? Maybe it's a branch predictor that looks at the last 5 values that were sent over the network or something. I don't know, but it'd be great to have some sort of interpretable description about what this thing is, so I can get my hands around it and start incorporating it into a new design.
Yeah, I mean, it gets back to, it was Brandon's question on Samira's talk, that maybe this is just a tool to help us think by generating random designs. And if we go to an abstract feature space into a semantic space, it gets at something like you're saying. It's maybe I don't generate hardware designs. Maybe I generate descriptions of hardware, of even English language, like you're saying, a branch predictor that looks at the last 5 jumps, something like that. Just to give us it's not a way to generate hardware, it's just a way to give jumping off points to designers and give us new crazy ideas. This is sort of a different proposal because there's still a manual design process, but it would be an interesting way to farm out ideas. It's like if you ever look at those random paper generators online, of to generate random research ideas, and you're laughing at them, clicking through, and then you come across one and you're like, actually, That's a pretty good idea. We should build that. You know, it's like that randomness can provide you good ideas sometimes.
Absolutely. Brandon has a question. Do you want to unmute yourself, Brandon?
Yeah, so I actually, I kind of disagree with the spirit of Adrian's previous comment. I don't think we want to understand how these things work at all. This sounds more like super optimization to me, where we just want to find the like mega hacked version of whatever we initially implemented, and it doesn't matter why it's a lot better, but it's just a lot better, and no one ever would have come up with that. So I could see that being, I'm taking an extreme position on this for rhetorical reasons, but I could see it being useful in that way too. Just treat it like a super optimizer. You don't really care why that sequence of weird instructions goes faster, but hey, it goes faster, so that's great.
I agree with both of you. I think we can approach this differently. I have a background in physics and formal methods for different things, so I always want to understand how things work. So I do agree a lot with Adrian that like it'd be really cool if we could understand how the thing works and then extract usable knowledge from that. But as an engineer, you're also totally right, Brandon, that sometimes it just optimizes and like you drop the machine and pick it up and it's dented, but now it works better. Okay, I'm not gonna question why. Let's just use it.
Great. So I got one question from Slack here. It's from Akil Giuliani, who says, how do you do a verification for such designs? My understanding is a verification time that causes most of the delay in developing new hardware. So one way of putting it is that most of the time when you're talking about like making hardware, which yes is like totally part of like a hardware designer's job. But another part of a hardware designer's job is doing verification. So do you have any thoughts about, I mean, one option is don't do verification, but do you have any thoughts about like how you might automate what we currently call hardware verification?
Yeah, that's an excellent point, that most of the design effort in hardware is not really design, it's actual design for test and the testing that you have to do, both in terms of VLSI testing and just functional testing and all that stuff. One solution is something I touched on briefly, which is if we operate, sorry, my dog is barking to go outside.
No, it's very
if we operate on a higher level feature space, not the level of gates and transistors, all of our traditional VLSI testing methods, to make sure we don't have fabrication errors or like logical errors, still apply. And if we have automated ways to approach those testing solutions, we can still apply those here. But we do have this big open problem, which is if we had a machine generate the design, we don't have a spec for it. We don't have a semantics. So how do we even go about testing it to make sure that it operates correctly? I mean, we don't even necessarily, when we first generate it, know what it does. We have to find a purpose for it. So the short answer is, I have no idea.
Great, so you got two more questions on Slack. The first one's from Diksha Dongwal, who asks, can we generate specs using this method? Will these specs be better than the ones we have today? That's related, of course, to verification. Yeah, so I guess is the question, if we feed in hardware designs, like we train the network to look at a design and then develop a spec for it? Or is this just like sort of Adrian's thing where we're generating random new semantics as a jumping off point for new designs? Yeah, good question. But like, you can feel free to unmute if you want to clarify. If Diksha's on the call, you can unmute. Maybe not. Okay, we should have a mic. So I guess of the two, if it's the first one where we're just, I mean, it's sort of a different problem where we're training the network to do something different. But personally, I think that would be a solution to a great, open problem we have, which is we build this hardware, but just specifying how hardware works is very difficult to do abstractly or in a usable way. So again, I don't know, but it sounds really good. Diksha clarifies on Slack, either. So great work answering your question. Irene Jing from Microsoft asks, can we meet the dog? Oh yeah, do you want to meet her? Yes, please. Oh, come on, baby. Let's say hi. Aw. That is a very, very cute dog. I really appreciate it. She's lovable. Well, thank you to Joseph.
I think this is a first. Wait, isn't this a first that we actually had a non-human in attendance in WACI? You might have been first dog attending WACI ever. So anyway, I expect you to interrupt your flow there. Sorry, Adrian.
No, I was just going to say, thank you to Joseph and also to all the members of Joseph's, human and otherwise.
Thank you.
Well, thanks to everybody. That wraps it up for all the talks. I want to give a couple of acknowledgements before we wrap up. I wanted to say thank you to the WACI co-chair, Christina Delamitri, who's on this call, and who helped me review a ridiculously large number of applications we got. We got 27 applications this time. So I also wanted to say thank you to everyone who proposed to give a talk, and we did not select. There were lots of really great talks that we, like, for one reason or another, didn't choose, but we're still like super cool. So I'm really enthused that everyone submitted. I also want to say thanks to all the speakers. So that's to Amrita, to Pratyush, to Samira, to Alon, to Joseph, and to Joseph's companion. I also wanted to say thanks to all the authors who couldn't quite be here. This was like a totally experimental thing, doing this synchronous wacky thing. It wasn't convenient for everybody, especially this week as everyone's personal lives are in total turmoil. So I wanted to say thanks to the people who couldn't be here, and hopefully we'll get a video from them or just a short paper to upload. But like, thanks to everyone who came, and thanks also to the people who, like, for very understandable reasons couldn't be here. Thanks to all of you. There are 60 people, above 60 people on this call. I was really enthused by everybody showing up and enjoying these really great talks. So thanks everybody, and stay safe and stay wacky. I'll talk to you later. Bye.